This video is for Trig section 7.1. Now, the overall goal of this section is to try to work our way up into identities. Now, this is a fancy word for trying to kind of clean up trig things like this. Now, a really true identity would be something along these lines where you already know something that's true, but you go through all of the steps to prove that it's true, kind of like a geometric proof if you took any of those in geometry. So you would already know what it turned into, but you go through all of the steps of these facts that you already know and put these pieces together to prove that this is true. Now, why we would need something like that is a lot of times we can make something that's much more complicated turn into something much simpler. Sometimes it might have helped to just kind of change forms. Back in the day before they had the super awesome calculators that you want to have handy, they might have had a chart of filled in values for sines and tangents and things like that, but maybe not for secants and cosecants. So it would have just been easier for them to work with numbers in this form than another. So they just needed to be able to go back and forth. So most of the ones we do are going to be to kind of simplify. So that's how we'll start out. And then we'll learn some later sections, some of these formulas that they found, these patterns. So they found that every time that they needed to do this with these trig functions, it always ended up being this. And so that's another reason they needed those identities. They got it down to this and they needed to see if they maybe could have put it in a different form and simplified that down at all. So we take together all of these little formulas and pieces. Like I said, you really want to have a note card handy on this one. And we build it into the big grand finale identities, like these guys right here. So to make it work with XYZ, I've turned them into matching problems instead of a more traditional identity where you already know the answer. So that's just kind of the outline of where we're going with all of this. Now, to kind of remind you of some of the principles that we use to work with these identities, we have just a little brush up on some algebra, so just to put it in a slightly more familiar form. So you, of course, would know how to factor this right here. This would be our difference of squares, and remember that the difference of squares would always break down into a plus and a minus. So x squared is, of course, x squared, so the front guys there would be x, and then 49 is 7 squared, so that means this factored out would be x plus 7, x minus 7, meaning if you were to FOIL this back together, the middle terms would cancel, leaving only the x squared minus the back 49 squared. Now, if I had fourth powers right here, I actually have another difference of squares. Now, 256 is 25 squared. Let me change colors just to make sure we know it's two separate problems. Wait, no, it's not 25 squared, it's 16 squared. There we go. And then a to the fourth is a squared squared. So it's the difference of squares just like our last problem. So that means we could actually break this down into a squared plus 16 and a squared minus 16. So from here, we're not quite done because we wanted to break it down as much as possible. And like I said, in these in identities, you'll kind of see why we need these steps. So right here, I do have this difference of squares. So this one right here is a sum, which cannot be broken down further. But this difference of squares is another a squared, and 16 is 4 squared. So I would break it into a plus 4 and a minus 4. So my final answer for this problem, the fully factored form, would be this right here. So remember that I could not break down this sum of squares, only the difference of squares. Okay, now if I had a big mess like this, I would want to try to break things apart, because remember we can only cancel factors. So I couldn't like reduce this 6 and 8 because they're added together. You cannot reduce sums, only factors, only multiplication. So I want to break this down into things that are multiplied together. Now the first guy right here is one of those difference of squares, so that would break down into a plus 3, a minus 3. The bottom right here, a plus 4, is as low as it can go. We can't really break that down anymore. This one right here, if you have your factoring skills up to speed, you would see that that would break into 2 and 4. 2 plus 4 makes 6. 2 times 4 makes 8. If not, you do have that factor program in your calculator that can kind of help you with that. And then this one, be careful of those signs. To make a multiplication of 6, I could do 1 and 6 or 2 and 3. I needed to have a difference of -1, so I would need a minus 3 and a plus 2. Okay, so then I'm going to break things down. It's all multiplied together, which basically means all of the tops would get multiplied together and all of the bottoms would get multiplied together. And then of course I want to see if I can take anything out, anything that matches on the top and bottom. So right here, of course, I have these matching a plus 2's, but then I also have these matching a minus 3's. Even though they were on separate sides, since it was all multiplied together, it all goes together. The tops are together, the bottoms are together. Now remember that I can only cancel the top with the bottom. If I had two matching things on the bottom, they would not cancel each other out. That would be like 1/2 times 1/2 does not reduce. That would be 1/4. Okay, so just be careful. I have to match top and bottom. I have one more that can cancel because these a plus 4's match up, which means the final answer is only the remaining a plus 3. Okay, so this right here was just a reminder that you do have to have factors to cancel them out. You couldn't just cancel individuals like this 6 and 8. And it makes sense if you knew what the numbers were. I know variables kind of make things confusing, but if I told you that I had 2 plus 3 over 1 plus 3, you would not think that that was equal to 2. You would know that that was 5/4, which actually does not reduce. So even though it might have looked like these 3's could cancel, the fact that they were being added completely changed the numbers. So they did not have a common factor of 3 like it might have seemed like they did at first. Now, if you remember back from your college algebra days, we had things like this, and there was a trick where we could take care of all of these denominators and just kind of clear them out. And I called it the Tylenol Trick back in the college algebra class. So in the very first lessons of fractions, you would learn that a fraction divided by a fraction needs to do the copy dot flip. So the first one would stay the same, you would copy, and then you would multiply by the reciprocal. So dot, multiply, and then you would flip the bottom one over, 9/8. Then you would reduce what you can, because just like the orange one up here, it's all together. So if 5 and 8 could reduce, you could. If 5 and 12 could reduce, you could. 9 and 12 do reduce. They're both divisible by 3. So it would be 3 and 4. And then even though 4 and 8 have something in common, they're both on the bottom. Remember, they can't cancel. So our final reduced fraction would be 15 over, is that 32? Sorry, double check myself so I don't mess anything up. Yep, 32. Now the trick was that to kind of do this all in one step, we could multiply both the top and the bottom by the common factor. Now in this case, I would need something that would cancel both a 12 and a 9. So the smallest number that would do that would be a 36. So taking this problem over again, if I multiplied both the top and the bottom by a 36, 5/12, and then a 36 times the 8/9, that would reduce the top one to a 3. So I'd have 3 times 5 is 15, and the bottom one to a 4. And 4 times 8 is 32. So just another way. Now you might say that seems harder trying to come up with the 36. In this case it might have been, but it's a much easier trick in these problems because otherwise you have to go through all of the steps of a common denominator, which I know is a little bit of a pain. So to do it the long way, I'd have to go through, get a common denominator, bring it all together, and then I would do a copy dot flip, and then I try to cancel. So here's where that Tylenol trick really comes in handy. So I see that the denominators, the little bitty baby denominators, are A, B, another A, and another B. So that means if I wanted them all to cancel, I could cancel them with an A and a B. So I'm going to put an A and a B next to each one of these 4 fractions. Because what I'm doing when I do that is I'm actually multiplying both the top and the bottom by the same thing. And remember that that's allowed. As long as I do the same thing to the top and the bottom, it's really only multiplying by 1. And then I'm distributing it to each of these fractions. So basically I put an AB next to each one of them because I'm doing a top and bottom and distributing. So AB times the 1 over A plus an AB times the 1 over B over an AB times the 4 over A minus an AB times the 3 over B. So notice it didn't change any signs or anything. I just put an AB next to each one. If you were working this on XYZ, I would probably just write down the problem with the ABs already there. So you wouldn't have to write it down twice. So then I go through and I cancel what I can one at a time. So in this first one, the A's would cancel, leaving just a B. The second one, of course, the B's cancel, leaving just the A. So it'd be plus A. On the bottom here, the A's cancel, leaving me with a 4 and a B. B4, 4B. Okay, and then the minus, and then right here the B's cancel, leaving a 3 and an A. 3A, and you're done. So lots of me kind of talking about why, but look, it was really just one step. I put all the ABs there, I canceled each one at a time, not trying to mix them together, and then I just found what was left. Now, as long as you pick enough Tylenol to make the headache go away. Now, if I'd only put an A next to everybody, it would not have canceled the B. So just make sure that whatever you pick to put next to everybody will make all of the denominators cancel. If by this next step right here you have any more denominators, these guys right here, you didn't have enough Tylenol. Go back to this step and pick your AB better, okay? Go back and see what you need to make everything cancel. So I'm going to show you what I mean in this problem right here. So notice all of these have an A on the bottom. Some of them have A squareds. Now don't write this down. I'm going to do it wrong on purpose here, okay, to show you what I mean. So if I thought just an A would make everything cancel, I would go put an A next to each one. So here's an A next to the 1, minus, here's an A next to the 1 over A squared, over, here's an A next to this one, plus, here's an A next to this 6 over A, plus, here's an A next to this 5 over A squared. Okay, I'm doing it wrong on purpose, so watch this. A times 1 would just be A, but right here, this would cancel one of the A's but still leave me 1 over A. So it's not better yet. I wanted all the fractions to go away. A was not enough. What I really needed to make all of these cancel was not just A, but A squared. Okay, now I don't actually have to do much to fix it. I just need to get all of these A's to be A squareds. Now remember, when I'm doing this, I'm just multiplying the top and the bottom by the same thing, the A squared, and distributing it to each one of these 5 fractions. 1, 2, 3, 4, 5. So everybody gets an A squared. So now A squared times 1 is, of course, A squared. These A squareds cancel. That leaves me with a 1 minus the 1. Notice now there's no more fractions. It's just the single whole numbers here on the top. Here's another A squared times 1. That would be another A squared. Now this one, A squared over A, doesn't completely cancel, but it would reduce. So remember, A squared is 2 of them, so one of the 2 would cancel. So that would leave me with plus 6A. And then the last one, just like the top, would completely cancel, leaving just the positive 5. Okay, now we're not quite done. We always want to see if we can reduce. This one has polynomials, which means they might have common factors. Let's break it down and see. This one would be that difference of squares. And then this one, to multiply to 5 and add to 6, I would need a 1 and a 5. There he is. Sure enough, there was 1 in common. So the final reduced answer would be A minus 1 over A plus 5. Okay, I'm sure you're thinking, we're in a trig class, why are we doing all this algebra? But it's all going to make sense soon, okay? Now, just a quick refresher on common denominators. Remember that if we had polynomials and we need a common denominator, we had to make sure that we didn't just get a y in common. It has to be the whole thing. So it has to have the exact same y plus 2. So these two already have that common denominator. So the only other thing I have to be careful of is I need to bring them together as a whole. So I have the 2y plus 6 minus the whole y plus 4. Now the reason I point that out is because I will need to distribute that negative. I was subtracting not just a y, but the whole fraction, which means I need to subtract the y and the 4. Okay, once I bring them together with that common denominator, they're both just over the same y plus 2. Now remember, I'm not multiplying. This one, I was multiplying, so I brought everything together. I multiplied them together. This one I was adding or subtracting, so I just needed the common denominator. This would be like if you had 1/4 and 2/4. Okay, if you had 1/4 of a pizza and 2/4 of a pizza, that means you would have 3/4 of a pizza, not 3/8. Those fourths would come together and combine in the same pizza box. Same idea. So in this one right here, after I'm sure to distribute that negative, I would get 2y plus 6 minus y minus 4, which then cleans up to be actually the same y plus 2. And we know that anything divided by itself is actually just one whole. So these matching factors right here would cancel, but be careful, they don't cancel to 0, they cancel down to 1. Okay, so that, like I said, is a little bit of algebra refresher. Let's do one last one right here. It's a little bit harder, just as a quick refresher for those common denominators. Now remember, we do need them to be matching, and they might have a common factor. So the first thing I want to do is see what's going on in the denominators. What are their factors? This one would be a plus 2 and a plus 5. This one would be a plus 2 and a plus 1. So luckily they have the a plus 2 in common. I don't need to add that in. So that means this one really just needs the a plus 1, and this one really just needs the a plus 5. And then they'll both have the same denominator. So let's do that. So in the first fraction, I'm going to give the top and bottom the missing a plus 1, because then the denominator would be a plus 1, a plus 2, a plus 5. Okay, so here's the original fraction, the 3 over a plus 2, a plus 5 in the factored form. Okay, here is me putting in the a plus 1 to make them match. Match what, you say? Let's keep going. This one, to make the denominators match, needed the a plus 5. So I put a plus 5 on the top and bottom. Okay, he already had the a plus 2 and a plus 1. So now you can see both of these fractions have the same 3 factors on the bottom. Here was the original fraction, 1 over a plus 2, a plus 1. Same thing, just in factored form. Original fraction, put in the new a plus 1, put in the new a plus 5, because now they both have the same denominator. So they're in a different order, but we know that's okay because they're multiplied and multiplication is commutative. You can switch it around. All right, so let's clean this up. Let's stick them together as one big fraction. So I would distribute this 3 right here. That would give me 3a plus 3. Okay, distributing the 3. And then this one, distributing the 1, would give me 1a plus 5. I can now bring them all together because they do have that common denominator. And remember, I don't write them twice. The common denominator just comes together, just like that last one. A plus 5. Remember the pizza. Okay, that's going to give me 4a plus 8. And then all of these, I'm not going to FOIL this back together, don't worry. I'm not that mean. In fact, I want this factored form because I want to see if there might be anything that could reduce. And sure enough, up here, I could break down, I could factor out a 4. And look at there, there's that matching a plus 2. Okay, see if I can write them small, fit it in here. A plus 2, a plus 5, which means my final answer after that a plus 2 cancels out would just be the 4 over the 2 remaining a plus 1 and a plus 5. Ooh, almost ran out of room. There we go. All right, don't worry, that's all the algebra for now. So the reason that we did that is because we do these similar things, this common denominator, multiplying each by the other one's denominator, stuff like that. But this right here, this is the kicker. This is the most important one. Being able to do this trick right here, multiplying it by what will make everything cancel. So the reason we end up with a lot of fractions is because, like we've already learned, secant is 1 over cosine, cosecant is 1 over sine, tangent is sine over cosine, and cotangent is cosine over sine. So they're all fractions. So that means we end up with fractions all over the place. So some other little pieces of information that can come in handy are the fact that cosine and secant are even. So if you remember, the even functions okay, hang on, I put them in here backwards. So the even functions would be the ones that have symmetry on the y-axis. You could fold them in half. So here we can see them. The cosine, I think I flipped them. Cosine and secant. Sorry, I have them upside down. So cosine and secant are even, which are these pictures down here, okay? And all of these are odd. So let me fix that really quick. All right. So your note sheet should be correct because I'll fix that now. So sorry about that. So the cosine and the secant are even, which means they have the symmetry in the y-axis. You could fold them in half. So you can see right here that the cosine curve that we just learned in chapter 5 could be folded in half along the y-axis. So what that means is that any value that you would pick over here on the right would have symmetry here on the left. Any x value would perfectly match up with the same number as a negative x value. So that is the even functions qualities. And then all of the rest of them are odd, which was the kind of strange symmetry that meant it could be spun. So basically, if I took this guy right here and I spun it over 180, so watch this curve, he looks exactly the same right now. So he looks just the same as he did before. So these are called odd functions. They can be flipped over 180 degrees. So any point that I found up here, x, y, would have a corresponding point, negative x, negative y. So what that means is if I had a point up here, like this guy has the point 1, 1, that means I automatically know there's another point on this graph as negative 1, negative 1. If I were to find another one, like this point right here of 2, 8, 8, then I automatically know there's another point down here of negative 2, negative 8. If I plug in the same x but as a negative, I'd get the same y but as a negative. Same idea here. So these pieces of information can come in handy. So right here is how you would kind of write that down. Plugging in the negative x results in the negative y. Okay. One other piece of information that really comes in handy is this one right here, the Pythagorean identity. Now it sounds like the Pythagorean theorem, and it's from that same piece of information. So we've already seen this before. We haven't really used it that much yet. So remember all those triangles we did in the first chapter. We found that the a squared plus b squared is c squared. Well, we said that the cosine is basically like the x value, and the sine is like the y value. So if I took the shorter side, the x value, and the horizontal side, the x value, and then the vertical side, the y value, and squared them, they would always equal the hypotenuse squared. Well, in the unit circle, the hypotenuse, the distance from the center to the edge of the circle, was always 1. So basically, we've seen this information before, we just didn't really think of it in this way. So we get to use these in all of our identities, because every time that I see a cosine squared plus sine squared, I can turn it into a 1, because whatever cosine squared plus sine squared is, no matter what the angles are, if they have that same angle, it would always come out to be 1. You could even test this in your calculator. So if you found the cosine of the angle, 56.387 and squared it, and then found the sine of 56.387 and squared it, and added those together, no matter what you picked, it would always equal 1. So it's just part of that unit circle and the fact that these form that right triangle. Now these are some variations of that same Pythagorean identity. Basically, if you divided everything by a cosine, this would cancel to a 1, sine over cosine turned to tangent, and 1 over cosine turned to secant. Same story for this one right here. So it's just some variations, but as long as you know at least this one right here, you're good to go. So let's try these out. So the first thing I always do in any identity is I switch everything to sines and cosines. That way there's just not really any sneaky things hiding there. So secant, I know, is 1 over cosine. And then cotangent is cosine over sine. And then looky there, just like we were doing with all of our crazy algebra review, I have the matching top and bottom. So remember, just like we did on that orange problem up here, that once they're multiplied, I can just bring them all together. And then those cosines that match up can cancel just like our algebra things did, leaving us with a final simplified version of 1 over sine, which has his own special name, which is called cosecant. So the final simplified version would just be cosecant. Now here, this example is actually just like this purple one right here. So it's a fraction over a fraction. Let's see how it works out. So secant is the fraction of 1 over cosine. And then tangent is the fraction of sine over cosine. Now I could do one of two things, just like I did on this one right here. So I could do the copy dot flip, or I could multiply both the top and bottom by whatever would make the denominators cancel. They're both about equally easy in this problem. I can see that they both have the same denominator of cosine, so I can multiply top and bottom by cosine. I'm going to show you the copy dot flip way just to make sure you can see both. So that would make the first one, the top, multiplied by the bottom one flipped over, cosine over sine. And look at that, it's actually exactly like the one we just did here in purple. Cosines cancel just like they did there, leaving 1 over sine, which once again is cosecant. All right, and last one. This one I have a little bit of a doozy. I've got secant, which is 1 over cosine. I've got tangent, which is sine over cosine. And I've got another sine. So what I actually have here is a common denominator already, because remember these can be combined. This one was just over 1. So I have 1 minus sine times sine is sine squared. Now, sine squared, just a heads up, in XYZ, when you want to write a sine squared, you will need to write it like this. Parentheses, sine of x, close, close, and then square it. Okay? But on paper, the way that we denote sine squared is this right here, which can be just a little bit confusing. We put the square symbol right here to indicate that it's the sine that is squared, not the x. So on XYZ, remember that you're going to have to put it in the parentheses and then square it to show XYZ that it's the sine that's squared. But on paper, you can kind of use this little shortcut here. So all of this is together over cosine. Okay, so all I did is I combined them because they had the common denominator of cosine. So I just brought this together to be 1 minus, and sine times sine made sine squared. But wait, we're not quite done. So this right here is actually that Pythagorean identity right here. So I already know that cosine squared plus sine squared is 1. You say, well, that's not what we have, but I have 2 of those 3 pieces. So some variations that come in handy are 1 minus the sine squared equals the cosine squared. And of course, 1 minus the cosine squared equals the sine squared. So there's going to be times that you kind of need to go back and forth between the two. And when you do, you just reverse it from kind of like its complement. 1 minus the sine squared is the cosine squared. 1 minus the cosine squared is the sine squared. So that means 1 minus sine squared from the Pythagorean identity is exactly the same as cosine squared. And now if I have cosine squared over cosine, that of course would reduce, because x squared over x would just leave a single x. So that would give us a final answer of just cosine x. Okay, So these are just kind of some little easy identities to kind of get you warmed up using all of these algebraic principles on our trigonometric identities. Now the main thing, like I said, is kind of manipulating this Pythagorean identity. This is kind of the new one. These don't come in as much yet. They're possible you can use them in some of them, but mostly it's going to be this guy, switching back and forth between sine and cosine. So just as always, let me know any questions you have.